Good morning, everyone. I'm Thi. I'm from Center of Sustainable Process Engineering. Today, I would like to talk about the hydrodynamic analysis of air, oil, water, separator under three-angular motion. This is my outline. The first introduction, the oil separator with compressor is one of the most important processes in the oil separation gas into separate gas, oil, water, and solid. The objectives of this study are to develop safety model for three individual and simultaneous angular motions, to identify hydrodynamics inside the oil separator, to predict the oil separation performance under three-shift motion. Here is a separator under shift motion. The typical motion conditions consist of three angular motion like roll, pitch and yaw, and three translation motions like church, square, and flip. You can see the separator under three angular motion in animation. Here is geometry. Inside separator included perforate plate, compressor, and demister. Here is the dimension for pallet scale oil separator. Next is meshing. The mesh type is a polyhedral mesh, and the number of cells is around 0.1 million cells. Here is a separator under shift motion. This one is the inhibitor under pitching motion. This table shows parameters for three angular shift motion. This one is the rotation metric. The rotation metric is used to calculate the angular velocity on the axis. The governing equations concludes continuity equation, momentum equation, and K epsilon turbulent equation. Here is a mathematical model for acid pressure control. In this case, the acid pressure control is used for both oil and water outlet with the same value Kb equal 50. This table shows boundary conditions and model parameters using in this simulation. Now we move on to result and discussion. The first part is safety result with the pressure control. And note the acid pressure of oil and water play an important role in maintaining the liquid level of oil and water inside the separator, which influences the oil separation efficiency. In this study, the acid pressure of water and oil was fixed 6.0 Pascal and 4.9 kPa respectively. Now I will show the dynamic behavior of the mass flow rate at the water and oil outlets. This case for water outlet, we can see here is a positive mass flow rate. It means the suction of water from the acid fiber, which is not realistic. We also can see the 4K pitching motion and three angular motion. The fluctuation of mass flow rate is bigger. We can see clearly that in the animation for pitching motion and three angular motion. So in the positive mass in water outlet. Next is the dynamic behavior of mass flow rate at the oil outlet. It's similar in water outlet. 4K pitching and three shift motion have a big hit impact on oil mass flow rate, and the rolling and yawing motion have no big on the fluctuation. This shown in the animation video. 4K yawing and rolling motion, the color of oil fluorescent dot change a little bit between the interface gas and oil. Now I will compare oil separation efficiency for no-rosin and ship-rosin cake. From this table, we can see the rolling and joining have no significant effect on separation efficiency, and for cake pitching and motion is decreases significantly the oil separation efficiency from 98% to 63%. So now, problem is backflow is not reality, and separation efficiency under pitching and remotion is too low. So now, how to prevent the backflow at the water outlet? So here is solution. Solution is acid pressure control, and I mentioned before, the acid pressure is controlled to keep constant the mass flow rate. Here is the result for safety result with pressure control. This figure shows the dynamic behavior of acid mass flow rate and acid pressure for no-motion cake and ship-motion cake. We can see here the joint motion, so the least fluctuation, and rolling and releasing motion indicate a static periodic fluctuation with a small amplitude than 2 degree pitching motion. Here, or 2 degree pitching motion. Next is the dynamic behaviors of acid mass flow rate and acid pressure for no-rosin and pitching motion cake. We can see clearly this for 4 degree pitching motion. The 4 degree pitching motion have a higher amplitude in acid mass flow rate and acid pressure at the water outlet than 2 degree pitching motion. Here is the comparison dynamic behavior of acid mass flow rate at the water and oil outlet with and without pressure control. This case for no motion, rolling and joint motion, the red does line for with pressure control. And this case for pitching and under 3 angular motion, we can see the acid pressure control eliminates the backflow at the water outlet. And the fluctuation of acid mass flow rate is much reduced in all cases with pressure control. You can see in animation in the below or with pressure control. Water outlet, there are no backflow here. Now we compare the separation efficiency and oil recovery of no-rosin and ship-motion cake with pressure control. This table, so we can see in the table separation efficiency of water at the water outlet high, normally high, except for the 4 degree pitching motion. This here. The oil separation efficiency at the oil outlet was high for all cases. However, the oil recovery of cake 4 degree pitching motion was low. Here, 93%, because the loss of oil from water outlet. And separator show a higher separation efficiency for 2 degrees simultaneous triangular motion. Here, now we move on to the conclusion and future work. This slide just summarizes some main points. The three-phase safety model was developed to investigate the effect of triangular motion on the separation efficiency and dynamic behavior of acid mass flow rate and acid pressure at the oil and water outlets under the ship motion was examined. The oil separation efficiency and oil recovery under the ship motion was ready, and the future work to develop a three-phase Eulerian safely with TPM model and to perform the three-phase Eulerian safely with TPM simulation under the 1 and 3 ship motion. Thank you for the attention and any questions.